Let's see. There it is. Okay, so we're into dynamics, content, and there once was a marker. However, I may go down the hall and steal one. I noticed there was a class maybe 2 doors down, so let me go steal it. Okay, so sorry I had to be out of town on Friday, but you got the email, so it wasn't anything. So this is the title rigid body, which means that the members are of course rigid and the distance between A and B remains fixed. So we learned, I wanted to say last time, but the time before last, that for purely rotating bodies, it's omega cross R in a vector descent. And then what we learned is the acceleration is equal to alpha cross R minus omega cross R, or, plus, or the same, he writes it like this. And so these are the same. Some people don't like it written this way. Some people like it written that way. But they're both the same thing. So where we're going to now is if this is a thing that's purely rotating, it turns out that if you're sitting on the body always appears like it's purely rotating. So if you put yourself and glue yourself to this point B, and this thing starts moving around, point B doesn't see itself moving. It looks out here and sees A, or in this case, he's got it written here. It's the position of B relative to A. It doesn't matter, it's the same thing, it's just a reverse vector. So this is the perspective. This person sees only rotation. And since he sees only rotation, these equations, from his perspective, fit him. However, he himself might be moving along and might have his own, will definitely have his own position, velocity, and acceleration. So it's just a vector equation. So you add the rotation that this person sees, the link taking place, and you add to that rotation his own movement. And so that's what happens in a few seconds. This is an interesting marker because it's square yet round. It's odd. So if you keep going down, you'll see he goes through this. Okay, and we're going to work the problem in a second. But let me get all this stuff out of here. Oh, maybe it's a permanent marker. That would be funny. So you see, okay, so he has a bunch of graphics, and what this actually is kind of showing you is that you can have plane motion, but if you take this and move it over, and then it rotates. So it's like, yeah, you went from here to here, this DR, you went from here, which is a different distance. So it's general motion in that this would have been general non-rotational motion. It just moves that way, but it's also spinning. So there's a lot of words to go with that. I would suggest reading those, but that's essentially what's happening. You get down here, and you see this is the person that's glued to A looking out at B. So it's due to the translation of A. This part's due to the rotation about A, and that's the general motion. So the benefit here is that this is due to only rotation. We have our equations like in the last section, or the section before last. The omega cross R goes right here when we get to the velocities. And that's what he's going to go do next. He's going to go do velocities. And then he does that. He says, okay, you got that. And I'm not sure why that's a capital right there. It's a capital right there, but it's not right here. So I think this is a typo. Smaller case, that's supposed to be smaller case. Because that, I don't know what happened. There's a lot of issues that happen when you produce information like this. You get all the way down, and you see this. And so what you see is you see a motion here that's due entirely by rotation, and then the movement of this person on A, and this is the rotation of what the person would feel if they were sitting on A looking at B, and that's the general motion of B. And so, let me see, I think I'll just go ahead and do an example here, because that's the best thing to do. Let's see how far I can go to get to the examples. Well, this is good enough. Let's just start here. Here's a link to blocks, or guiding, or in guides A and B, moving with fixed slots. If the velocity is 2 in this A, down determine the velocity of B. That's too easy, but I'll do it anyway. Okay. So velocity of B is equal to velocity of A plus velocity of B relative to A. And so now these are vector equations. So I need to take off the 2. It becomes, I'm going to go ahead and put in the 0 just because. Plus, now I'm going to say omega cross R B to A, and that's equal to velocity of B. That's an equal sign. Now, the way you do this, there are 2 ways. He does it in a book one way. I do it a slightly different way. Here's the way I do it. Okay, first, I'm not going to address that one until I address this one. So I'm going to draw a vector that originates at A, goes down here, and hits B. So this R B A is going to be, it's 45 degrees. It's got it kind of buried right in there. And it's 0.2. So it's 0.2. Okay, so here's the thing. Cosine of 45 is equal to the sine of 45. That's the beauty of it. 1 over square root of 2. So I'm going to put that over square root of 2. And that is, here, here's my X, and here's my Y. So that part is up to here, and then it comes down to here. So you get the X component going out here, and then you get the minus 2 over 32J. Just a simple thing. So now, I always do this. There's like a whole bunch of marks on this table. But it's dry erase, so the thing is now, I do not know omega. And technically, although he doesn't do it, and I didn't do it, I'm going to start doing it as quick as I can and say it's the omega of link AB. It's the only link there, the only rigid link, but later there'll be 2 or 3 rigid links. So I better just go ahead and start this, that this is the rotation of AB. In other words, if you were sitting on A, you would go down and it would look like the thing is rotating like this. Now here is where I did do that right. If I don't do something right, you speak up and tell me. If I have not had any caffeine yet today. So here's my X, here's my Y. It turns out this is a plus rotation by the right-hand rule. Meaning that if I take my X cross, it's coming in a Z. This rotation is positive. That rotation is negative. So this is a definition of the coordinate system. So if I don't know the rotation, I always represent it as being positive. Now, I can go down here and do this minus 2J plus, and here's what I always do. If you look back somewhere in your past, you would see this, where you set up this determinant, and let me write all the numbers, and then I'll go back and address everything. First thing I'm going to address is, of course, the first row. I mean, you've seen this where you do IJK, and then you're going to do cofactor expansion. The second row is the first item, and the first in the cross part. The second is the second item. Always happens that way. The thing about the first one is there is no X rotation, meaning it's not spinning this way, and it's not spinning about that axis. It's only spinning this way. This thing is only spinning that way. So there's no X component, no Y, and there's only Z. Now I assume it to be positive, so to me, this rotation like this is going to be a positive number there. If I want to assume it to go the other way, I'm going to have to keep a negative sign, and I'm going to have to keep up with that. So I don't want to keep up with that. So I always assume everything's positive. That could be a saving grace for you in a situation like that. This is, of course, the R vector. It has no Z component. It has this and this. Now, what I know about B, this B right here, is it has to either, this point B, oh, there's the B right there, is that it has to either go to the right or the left. I'm just going to assume it to the right, and I'm going to say a scalar value times I. So now I have an actual vector equation. So if you do this cofactor expansion, I'll do it this way. Minus 2J, and then I'll do the cofactor expansion plus I, and I'll do it complete. Even though there are terms that minus 1, 2 over square root 2, and then minus, because you got to do a minus on the J. And then you just eliminate that, and you get a 0. B, that one, and this one. Now, I'm going to do the K, even though there is no rotation, because that cofactor expansion is here, and I'll explain that in a second. Okay, so if you look at this, why does this end up this way? So if you're just stare at this and think about what this actually means. This is the rotation or the velocity of point B if you were sitting on A. Maybe I'll redraw the link. And so here's the link. No, that's terrible. But here's A and here's B. And I'm assuming a positive rotation. So you can put it right there. I'm going to try to make this look a little bit better. Or, it doesn't matter, put it right here. So in that particular case, I would see a velocity that would look like that. If you were on A, and if this was rotating this way, in this sense, what this means, omega AB cross RB to A, means you are sitting here in a way you are pinning yourself to the ground when you're rotating that way. Even though I know this thing is translating this point and moving down, the person that's sitting there sees this. And consequently, since it's rotating only about this, it's not going into the board, meaning there isn't a K component of this velocity vector. There's only an X component out here and a Y component out here. The X component here comes directly from this, which we'll do in a second. And the Y component comes directly from that. So let's do those two. And what we'll see, I'm going to redo this. I'm going to do it like this. 2 minus 2j. And I'm going to do the cross product. This comes this, minus that comes that. So it's a minus, but there's a minus sign there. So I'm going to get a plus omega AB, whatever that rotation in radians per second is. And I guess I'll put the 0.2 in front of it. And I'll put the square root of 2 under it. It has the I associated with it. And now I'll do the J. I'll put the J here. Now, there's a minus, okay. 0 times 0, 0 minus, this one comes that one. But it's a minus sign in another minus. So I get 0.2 omega AB over square root of 2. First of all, it just makes sense. If you look at this, it's a positive. That's the first thing to look at. Okay, that is, when I draw this and look at it and think about it, yes, that's positive. Yes, this is positive as well. So I'm comfortable there. However, there is a third way to check this. That is, that dates to your Cal 3, I think. And if I take any two vectors, I'm going to try my best to draw two vectors here in the plane, AB, and I cross them. Let's say I cross C is going to be A crossed with B. So take my fingers, I stick it out A, and I rotate towards B, and I find this new vector C. One of the things about that is that A and B define a plane. It turns out that vector C becomes perpendicular to both A and B. So again, if you had two vectors that are sitting here, and they could be sitting in any orientation in space, if I cross the product, the vector that's come, the cross product vector is perpendicular to both this one and this one, no matter how oriented. With that in mind, what would you say C dotted with A would be equal to, and C dotted with B? Okay. This is a cross product, gives you back a vector. Dot product gives you back a scalar. Any idea what those two are? There's the magnitude of C, magnitude of A, comes the cosine of the angle between them. So it's just always 0, right? That's the definition of that. So by nature, it's the same thing where you say, oops, I dot j, that's equal to 0. I dot I equal to 1. I dot k equals 0. These I and the j are 90 degrees apart. Cosine of that 90, your 90 starts up here, your cosine starts up here, drops to here at 90, drops again, comes back up to here, and then it starts over. It's 90, 180, 270, 360. So in fact, if you took a vector which was generated from a cross product and you dotted that vector back against either one of these, you should get a 0. Now with that in mind, let's take a look at, hang on, this is easier to do if it was online, but because I could just move this out of the way and now it's going to disappear. So here is essentially my result. These are the two vectors, this and this. First of all, if I dot the first one, okay, now this is going to take a few minutes. If you dot the first one with the first row, you're dotting omega and here. This is a way to check it. This is all I'm doing. Is I'm saying in the middle of working a problem, some of these problems will become very long. If they become very long, if there's a way to check them as you go through, it's to your benefit to check them so you don't find out you've worked a big long problem and then you got to go back and find where you made the problem, where you made the mistake. So what this is a kind of a diagnostic. So this is the result. If I take this vector, which is some kind of, well, actually, so this is my C, this is my A, this is my B. So if I take this one and dot it with that one, I should get 0. Okay, let's look at it. Okay, I'm going to look at it in here. 0 times that, 0 times that, and I might as well say, because I didn't, okay, that times that times that gives you 0. So technically you got this term. So technically you have that term as well. That's a no-brainer. This one always, this doesn't help you diagnose stuff that well. The second one, the vector here, does help you diagnose it. And it helps you diagnose it in this way. So I got 0.2 over square root of 2 times this, plus a minus 0.2 over square root of 2 times this. Turns out they're equal magnitudes but opposite signs, and they cancel out. So this might seem like I'm stopping and saying, okay, we're working part of the problem. It's not crucial to the problem. However, I've said this many, many times, you should expect to always make mistakes. And so you should do your work, whatever you're doing, in such a way that you can find your mistakes. So you take your time a little bit, you go through, you're putting it down on the page to diagnose your own mistakes. So often, I'm not trying to, but I've seen people, come in, and this is the reason I switched to this textbook stuff. You produce a lot of stuff and you put it out and you say, is there any way you can give me partial credit? That's fine, I understand that. But when you do that, you're missing the critical part that when you leave the campus, you're going to have to diagnose your own stuff. So you might as well get used to doing that now. So that's one of the things I try to do along the way, is to help you find diagnostic ways of solving. So in effect, here, I think I erased or never wrote this. So in effect, we diagnosed this, and at least we passed the 2 tests. The one test is drawing the object It's rotating this way, and we know our velocity vector is that way, so we know we have a positive sign and a positive sign. We met that sort of test. The second test is I always take what I get a result and I dot it against this one. I don't really spend much time here because that doesn't give you a diagnostic, but this one does. And so you go through this, and now you have two equations and two unknowns. Actually, if you don't mind, I'll go ahead and erase that because that's not crucial now. So if you look at the I equation, in other words, this one and this one, you get, hang on, give me a second, VB is equal to 0.2 mega AB over square root of 2. And then I look at the J equation. On the left-hand side, I get nothing. Right here, I get 2. So I could move it to the other side, but I'll wait a minute. Plus 0.2 mega AB over square root of 2. If I did move that to the other side, I would notice something interesting. I would notice that these two terms are exactly the same. And so you're going to basically come up with the velocity of B. Actually, this should not have a vector symbol on top. It's the magnitude of the velocity at B. It just becomes 2. Now, let me show you the way he tends to do it. Unless he's changed the way he's done it, let me show you the difference. Okay, first thing, okay, so he is actually going to also find the velocity at C, which we'll do that in a little bit, but he's doing it this. He puts his coordinate system on it. He does his little rotation. It's 45 degrees, so he has to come up with this. And in order to not make it so busy, I'll go ahead and drop the, and then I'll move it back up. So he has this picture right here that he's split away from his original picture. So give him a second to my stuff on this. And then what he's going to do, he's going to break down the equations, I'm sure. Oh, but he does it in another space. Here's what he does that I generally don't do. So he's redone this picture again. I'm not sure exactly why, but he has the equation sets, right? He says VBI, VB has to go that way because it's in that little slot. So he copied that down. So he recognized this, and then he does this, where he does omega times k across that. Now, that's okay, but to me, I visually don't see the structure. So here what he does is k cross I, and then he gets that off, and k cross j, and that'll end up being a minus. So you got to keep track of the I cross, the base vectors cross with each other. If you can do this, that's fine. I have found that people who try to do that tend to make a few more mistakes than actually using the cofactor expansion. It's the exact same thing, but then he goes through and he puts a big space in between everything. He has his two equations, and I didn't find that yet, but I found the answer there because that's what he's looking for. But you can find that by going in to the one equation back there and taking it out. In other words, this equation right here, you can find omega AB and put it back in here, but I recognize it. I mean, if it's 45 degrees, I recognize. Now, I don't know what he's got down here. Okay. I think he has two different ways, but I have a third way. But I like to use my way. We all like to use our own way. You may find that your way of doing this, you may feel more comfortable about doing this. However, what you find out is this is going to look really weird. almost laughable what I'm about to do. But if you do, say, I cross J, and you list it, your first vector is I, your second vector is J. You can do the cofactor expansion and figure that one out. The only one that's going to have one is going to be the K. Then, so you're going to have a cofactor expansion, 1 times 1 minus nothing times nothing. Then do this, and what you'll find is this. The J comes first. Oops. And then this one. Now, if you do a cofactor expansion with J, here's what you find out. I mean, with the K, you remove this, you remove that. And so the only thing you have is a K times 0, 1, 1, 0. This time plus minus, so it becomes a minus K. So J cross I equals that, I cross J equals to K. So if you have trouble remembering those, you can go back to the cofactor expansion, but if you're going to do that, then you could list them that way. So I don't know which way you feel more comfortable with. He's presented it in this way. This other way is something new that I have. This is the way in the old textbooks he's been presenting it for decades now. It's okay, but I can visually see things here. There's another reason I do this, is because this structure is exactly what shows up in the acceleration. So if you have this structure visible on your page, you can recopy it in the acceleration and just change the omega to an alpha, and you get the same, So to me, I visually see a structure that I can pin everything on. I can see my rows. I can see how to dot this with this to check myself. Then I can move on with a little bit of confidence that I go through the problem and I'm okay. And so this is the way I do it now. And there's, multitude. The other thing I like about this is that you can draw up in MATLAB and do a cross product. You can come up with, you can use symbolics to do this. I might as well do it. It's kind of, now, I don't know how comfortable everybody is with MATLAB, but there's a course on it that you got to take eventually anyway. So let me just show you. Okay, so it's taken up. So I can do that so I can visually look over here. So actually though, it looks like, here, make it take up the full amount of the screen and still have it so I can see the left. I'll do it like that. So if you end up, you can say SYMS. Okay, what I'm doing here is I'm creating a symbolic variable. And I want to have two unknowns. And I'm going to have this and this one. VB, I'll just call it capital VB. And then I'll just call this capital omega, little a, little b. And so if you do this, VB and omega AB. So you wait a minute, it takes it a minute, and then if you look at VB, oops, you just get a symbol. The beauty is I can put all this together. Here's what I mean. I'm going to write this equation this way. So let me write it one step up here. And I know I probably shouldn't do this, but I'm going to do it anyway for those. I mean, have y'all done MATLAB? Have you at least seen it before? So here's what I'm going to do. I'm going to take this as a vector. Oh, sorry, PB. I'm going to take that as a vector, which I'm going to define as this term, and you'll see me define that. And then I'm going to cross the omega AB with the R B to A. And I might put them on the other side. I might take that VA and put it on the other side and call it an equation. Here's what I'll do. Equation, EQN equal to, here, I'll put it over here as a minus VB. So the equation has to be EQN equal, the eventual thing is this equation has to be equal to 0 for this to be satisfied. So let's take a look at this. And you'll see kind of, first of all, I need to define my vector. My R, I'll say BA is equal to, and the vector is 0.2 over square root of 2. And as a vector, it needs another 0.2 divided by square root of 2, and it's always going to have 3 components. So, oops, I forgot to put a parenthesis. Oh, that's supposed to be square root of 2. So there's my vector. I know it's getting busy, so here, maybe I'll take this out. I hope I'm not erasing something I'll need. So there's my vector R B to A. Now I don't know omega, but I'm going to make this into a vector. Okay, and so before, you know what I did is I made it a symbol where it was that. I think I'm going to lowercase it. And then I'm going to say my omega AB is equal to, and it has nothing, nothing, and omega AB. So it's pretty boring in that it gave me back this, and this. So now I've got this. I'm going to do a cross product and see what this looks like. Omega AB, but let me do the cross AB with R, wait a minute, what was it, BA. So there's my vector. Now if you look at it for a minute, you're like, oh, this looks weird. But in fact, and unfortunately I just erased it, these are the two terms that ended up coming out of this equation. In other words, well here, I'll go one more step. And the last step is this. If I want to do this, I'll take the cross product. I'll add a VA, which I haven't actually defined yet, which is this. But I better define that first. VA is equal to, it's going straight down, so it's 0, minus 2, I think, and 0. There's your VA. And my VB, okay, so I'm going to go ahead and do a symbolic and change that one to a lowercase as well. And I'll say my VB is equal to, it only goes to the right. So this only goes to the right. So it'll be a symbolic VB for the I component. Nothing, nothing. Now I can write the equation. EQN equals to, and what I'll do is, the first one was, I'll say VA minus VB, and then VA minus VB plus cross RAB, but the omega has to come first. Omega AB cross that, which this is VA, but I've got to cross that omega AB, I believe. And so I get an equation set. Now, I'm going to try something weird real quick. Okay, so this is the x equation. This is the y equation. This is the z equation, which doesn't give me anything. And so let's try. I know in the old days, I used to be able to do this. EQN. I don't know if it happens anymore. Now, looks like it does. So there's your solution. So now S dot VB is equal to 2. S dot mega AB equals to that. Now, if you want to see it numerically, I think, oops, is it, okay. I'm getting my languages confused, but I may be, no, that's okay. So it's 14.14. We look back at the book. Okay, I have to scroll around till I find it. Where was the solution? Oh, there it is. Yeah, it's kind of buried right here. It's 14.1, and it's rotating in a positive direction, so that's why I got a positive negative. So I got the right answer. So you can actually do the whole sequence in MATLAB if you break them into vectors. So I don't know, that is so he has one way, then two way, then I have a third way, and then if you want to, you can use MATLAB to go through this. SYMS will turn something into symbolic, and then the solve will solve the thing for you, as long as it can be solved, as long as there's a way to solve it. Meaning that you can't have too many. You can't have too many unknowns than you have equations. Otherwise, it'll give you an error that you don't have enough equations. So what we'll do is we'll do more and more of these until it becomes comfortable. Then you'll have a whole set to do. Then we'll go into instant centers, which actually helps a lot. And here's a set of problems. So what we'll do next time, we'll just start working on these problems. So you can see they're all rigid bodies. In this case, there are two of them. There's a link here, and there's a link here. This is just one rigid body. The ball is just one rigid body. Here is two of them again, AB and BC. You can have more than two. I'm looking for one with more than two. That actually has a link here and a link there, so it might look like it's more than it is, but it's not. Here's a case where you've got three. You got a rigid body here, a rigid body here, and then a rigid body here. But it turns out that there's an advantage to using the equations the way we do. You can solve as many as you want. So, oh, there's another one. 1, 2, 3, 4 rigid bodies. I can't tell. That might be just two rigid bodies. And that's the extent of the process. So we'll come back in and work a bunch of those. The homework for next weekend, I don't know that I put any of these in there, so we'll see how that goes. I'm not going to go back and adjust, but they'll end up in the next week assignment. Yeah. So might be a week ahead. So did this kind of make sense? And then we'll look at some. Here, let's see if I can find. Let's see if I can find linkages for old. I'll look around. There's a linkage system. Linkage. I don't know. Old movie projectors. How about that movie? Okay. Maybe they'll have something like that, but you know, it depends. I'll look inside and see if I can find one of these ones with the linkages on it. Okay, let's see what this mechanism shows linkages used in an old movie projector. Okay, I don't know what that is. Oh, that's on Chegg. So essentially, it's like a 4-bar linkage, in which, if you think about it, this too much equations on there. So if you think about it, this one's a little short thing, so it just goes around and around. This one just rocks back and forth, but it basically keeps it as this thing is down below here. This thing evacuates the film. So in essence, this is a mechanism that turns rotational into intermediate linear motion, meaning that this there's obviously a motor connected here spinning this thing, and so it pops out. There's a mechanism, there's a way you can plot its path. It'll go in and pull the film and then drop out. And so there's a lot of mechanisms like this out there. And this is just one of them. There are a multitude of things. It doesn't have to have just 1 and 2 and 3. You can have 4, 5, or 6 linkages and have all sorts of weird patterns that you want the tip, this P, to behave like. Maybe you want it to go over, sit there for a second, plunge down, pull it, stop it, pull it again, and then drop out. There's ways you can design things to do all sorts of weird behaviors. So we'll just go from there. I'll come back and work more problems next time. Well, that's right, let's see. So she's got this lecture after me. So I got to give her a properly working computer here.